This is me.
And this is me too.
Baffled are you? Don't be. This really is me.
And I am his twin. Me too.
I'm Mr. Yes. And he is Mr. No.
I'm Mr. Zero. And he is Mr. One.
I'm on. And he is off. Just two words.
But together, we two make a complete language. A language so powerful that it drives your world.
Computers are powerful. They rule the world. Education, offices, laboratories, hospitals, transport, even shopping and entertainment. Just nothing works without them. They are everywhere. But what are computers? And what goes into their making? What is the language that these wonder machines understand?
So what makes the computer a computer?
Well, we, the binary twins, are all set to take you on a journey into the world of electronics. Bits and bytes, chips and circuits, switches and logic. The world of electronics, where we live. We all do.
For I am Mr. One. And he is Mr. Zero. But for now, we will get together.
As we go for a unique discovery into the world of electronics.
The Visvesvaraya Industrial and Technological Museum, Bangalore. The BEL Hall of Electronics is a very special place, welcoming the visitors with digital shadows. Here, in the world of electronics, technology springs to life. Some inventions are more special than the others. Their impact immense. The year 1947 was momentous for electronics. The invention of the transistor by Bardeen, Brattain and Shockley changed the face of electronic machines forever. To understand how, a look at the ENIAC, the world's first computer. Weighing nearly 30,000 kilograms, the ENIAC was massive, occupying nearly 680 square feet area. When it was switched on, the lights in the neighborhood dimmed. And today's computers, from desktops to laptops and palm tops, their size keeps decreasing, but their ability to work keeps getting better. It is the transistor that has made this possible. But what is a transistor?
A tap. It's a lot like a tap. By opening or closing it, you can make the water flow or stop. You can even decrease or increase the flow of water. A transistor can really be thought of like a water tap.
The tap can be turned on and off to run or stop water at will. A tap can even control the amount of water that flows from it. Replace the water with electronic signals and you have a transistor, an electronic component that can change and control electronic signals. It can work as a switch, an amplifier, and even an oscillator. Let's quickly see how. A transistor is like a three-layered sandwich, either a negative-positive layered one or a positive-negative one. When a small current is applied to the central layer, a much larger current can flow through this sandwich. This gives the transistor its switching behavior and also the ability to turn a small current into a much larger one. So, it is the transistor that has freed the computers from the bulky vacuum tubes. Because of them, computers have become smaller and increasingly efficient. Computers take the input, process it, and return it as output, millions of times per second. That's how efficient they are. The input and output devices work simultaneously and efficiently to perform varied tasks. All data entering the CPU through its millions of gates, getting processed and transferred in no time. This, in a nutshell, is the basic job of a computer. And now that we're talking basics, time we quickly understood analog and digital. A simple example, an analog clock is the one with hands. The time varies continuously without stepwise increments. Sometimes the arm may be between divisions. The digital clock is quite different. Its display has stepwise increments, fixed quantities that do not vary, showing the exact time every time. In analog technology, a wave is recorded in its original form. Like here, the sound wave is taken straight from the microphone and sent in an electrical form. It goes up and down continuously, always varying. In digital technology, the analog wave is sampled at some interval and then turned into numbers. Just two numbers, 1 and 0, on and off. This is the binary language, the versatile language of zeros and ones.
Hey, Mr. Zero! What is a computer? Huh?
Computer.
Yes, a computer.
A computer. A computer is thousands to millions of switches connected together. And you can replace the word switch with transistor. How's that?
As good a definition as it can get, huh? But how do these millions of switches or transistors sit inside a small computer, huh?
Are you testing me? Huh? I'm insulted. I'm going to take a chip break.
Where there is a computer, there is a chip.
A chip, microchip or integrated circuit, the brain of electronics. Anything that uses electricity and can be told what to do has to have a chip inside. A chip holding thousands of transistors. Transistors acting as switches and amplifiers. Computers can be made to perform intricate jobs at amazing speed. At the BEL Gallery, the entire process of chip making is on display. From sand to the chip, it's a long journey. Sand, one of the simplest and most abundant things on earth. It is from sand that the making of the chip begins. It's an intricate process involving a lot of physics and chemistry, heat, ultraviolet radiation, polishing, cutting, nearly 350 processes. Precision and extreme cleanliness are a must. A single speck of dust is enough to ruin the chip in its making. Sand is heated to a very high temperature and purified. Silicon is now molten. A single crystal, a seed, is brought in contact, rotated and pulled out. The result, an ingot. The ingot is sliced using diamond saws. Diamond, the hardest substance known to man. From glass to metal, it can slice and cut all. The wafer is thin. On the wafer, the first layer of silicon dioxide is grown by exposing it to extreme heat and gas. This growth is similar to rusting, a layer so thin that it cannot be seen by the naked eye. The wafer is then coated with photoresist that becomes soluble when exposed to ultraviolet light. Masks of required circuitry create patterns this way. The softened photoresist is removed. The mask is also etched away. This leaves a 3D pattern on the wafer, the pattern of a circuit. Now comes doping. Doping to alter conduction properties.
That's smart. P-type does mean positive. And to quickly remind you what this means, this is one with a deficiency of electrons. The N-type, on the other hand, has excess free electrons. But coming back to the making of the microchip, it is a cumbersome process.
The making of a chip takes 4 to 6 weeks. The cycle of film deposition, photolithography, and film removal is repeated over and over again. The ready transistors need to be connected. Another complicated process with many levels of metal wiring. The final combination of the transistors and interconnects is the microchip or the integrated circuit.
You must have understood that several microchips are made on a single wafer. This entire process needs testing, and some more testing. Each stage is monitored closely. Even a single defect is not acceptable. But let's talk some numbers, some amazing numbers.
A single chip in the Intel Pentium 4 processor has 42 million transistors. 42 million transistors sitting on a chip. And now, as the years go by, the size of the chip keeps shrinking and the number of transistors on it keeps increasing. Dual-core Intel Titanium processor has 1.7 billion transistors. The pace of growth in electronic technology can be understood by the mere fact that Moore's law has held good so far. The co-founder of Intel, Moore, had predicted that the transistor density doubles every 24 months. You can imagine what the future holds. Or can you? How small is this? A micron is 1,000th part of a millimeter, 70 times smaller than the width of a human hair.
Anything for science. 1 nanometer is 1,000th of a micron, and that is... Excuse me! At the expense of my hair, it's only fair that I do the talking. 1 nano is thousands of times smaller than my hair.
The smallness of the integrated circuits makes them complicated, and complicated they are. The electronic signals pass through them at lightning speed, carrying out multiple tasks at any moment. They appear to think, but think they do not. They simply talk a very special language, the language of on and off.
Off! That's me, Mr. Zero. And on is me, Mr. One. Did we not say we are the most powerful language in the world?
The language of electronics, binary, where there are just 2 alphabets. 2.
It's simple. Yes, yet not so simple. Go ahead and type A on your computer, huh? Go.
This is what the computer changes the A into. A sequence of zeros and ones, a combination of 8. This is the world of binary language. Remember that all digital machines use binary to store and process data. At the interactive display, the children play with beads to create alphabets in the 7-bit ASCII code, a language of binary. Here the white bead is 1 and the black 0. As the visitors drop the rows of binary alphabets, the sensor inside reads it aloud.
I'm 0. I'm no. And I'm off. Wherever I am, there is no flow of current.
I'm 1. I'm yes. And I'm on. I let current flow. Let's simplify, huh? Simplify. Think bulbs, a sequence of bulbs. Bulbs that go on and off, and you will know binary.
If you had just 2 bulbs, these 4 would be your only options or possible combinations. First on, second off. First off, second on. Both off. Both on. This is the foundation of binary language. Sounds complicated, but it's not. Binary, the smallest numbering system that can be used. In binary, each letter is converted into a sequence of 8. So any data on the computer gets converted into the binary code. Each letter or number, a set of 8. Each byte is an 8-bit binary code. So the word bits itself would be 32 bits. May appear cumbersome, but there is tremendous logic. At the PEL gallery, the visitors move a step further into the world of logic gates, the building blocks of digital circuits, combinations of logic gates from circuits designed with specific tasks in mind. Most logic gates have 2 inputs and 1 output. In the AND gate, both inputs have to be on to allow the current to flow. This is the OR gate. Here, either of the inputs, the strings in this model, can make the current flow. They can be thought of as 2 friends working in coordination. The interactive model displays flip-flop. Flip-flop switches from off to on with a short input pulse and then stays on. They are the most useful in storing inputs in memory chips.
But now, time to go shopping. But here in our binary world, we will talk in my language only. What say? Yes or no?
Time for shopping. Time to visit the mall at the Hall of Electronics. Time to understand the barcodes. Those strange light and dark lines that are used for billing, you must have guessed. The dark line creates a high and the light one creates a 0. When the sensor picks up the code, all the stored information appears as if by magic. The name of the product, even the price. So barcodes are nothing but product information stored in binary codes.
If I was here, but I felt I was there. If I was touching nothing, but I was touching that, what would you say?
I would say that you have gone bonkers.
But I would say that I am in the zone of virtual reality.
Volleyball without a ball. A match with a computer. Virtual technology can make the unreal real. It controls what you see and respond to your movements and actions. At the BEL Hall of Electronics, the virtual zone is a huge attraction. It's science with fun. The science of electronics, a window to the potential of future technologies. It's the wizardry of electronic circuits, cameras and sensors. Here, sounds increase the experience of reality. The matches become exciting and champions emerge. Virtual makeover to change the way you look. Grab your picture and use your imagination. You can grow a beard or change your hairdo. Visitors enjoy hands-on science. Maybe the right place to style your looks before a visit to the barber.
Electronics rule your world. It is everywhere.
Simply everywhere.
So we hope you have enjoyed the journey from the transistor to the microprocessor. Have you?
For one, I will say yes. But I am no.
And I am yes. But I will say no more. For it's time to go.
Bye.
Bye!